All right. So, thank you everyone for virtually coming to our little presentation today on writing efficient R code. This is probably going to be a little bit less than the 2 hours we usually schedule, just because I've found that I get fewer questions and discussion on Zoom calls, but I'm happy to be pleasantly surprised. My name is Ben Evans. I am a computational research support analyst at the Yale Center for Research Computing. And what that means in plain English is it's my job to help people do the research on computers. And we spend a lot of time at the Center for Research Computing helping folks do the research on the high performance compute clusters that we help to maintain. But today, I'm hoping that the lessons learned will be applicable both to R code that you run on the clusters, but also R code that maybe you're developing just on your laptop. So I'm going to start out just with some general tips. These should even apply to your, oops, I have an overlap there. You should even apply to code that you're writing in other languages. And then a few tips on performance that are R specific, a little bit of review on R's vectors and matrices, which are two sort of basic building blocks that you would use a lot in R if you are not already. And then talk a bit about R's memory management, that is how it stores the data that it's working on in your computer's RAM. Then I'll go over a little bit about profiling and benchmarking, the difference between those two things and what they are, and then talk about loops. And again, if you have any questions throughout, feel free to click the raise hand button if you'd like to speak, or type your question in the chat, and I'll try and get to it as soon as I notice. And let me know if I'm going too fast or too slow. So starting off just with some general advice. One of the great things about R and other languages like it, kind of like Python would be an example, are that experiments are really easy and fast to prototype because the language is built around the idea of you having an interactive relationship with it. So in all of the interfaces to R that you might use, either it be just the pure R command line interface or something like RStudio, you have a shell that is accepting R as commands, and so you can test out functions and such in a relatively quick and fast feedback sort of way. So I find that I understand things best when I start to break them, but you know, do your own experiments and find the ways in which you can explore different functionality. I know it can be slow at first, but it really comes with a little bit of practice. The R documentation is not my favorite. I don't think it's anyone's favorite, but to learn a little bit of its jargon and to sort of supplement the built-in documentation with Google searches is really how you can build out more of your knowledge about both the R standard libraries and the libraries that you might begin to use on top of those. When you're writing your code, and this is a good idea, again, in a lot of languages, is to break your code into sort of modular pieces that you can collect in R as functions. And in doing so, it helps to separate out your code in more digestible pieces, sort of for your brain, but also when you go back for troubleshooting, or if you do want to try and optimize your code for speed, it really helps to identify sort of different places in your code if it's broken into functions. If you begin to share your code, or if it begins to be used by other labs, other groups, it's also great to write tests for your functions. And these can be as simple as just like a comment at the top of a script that says, this function should return this result if it's given this input. But there are also packages that can help you be more structured about that. But just to keep in mind that it's great to be able to test your functions to know that they are producing the desired results. We at the YCRC really encourage the use of Git for keeping track of the changes that you make while you're writing computer code. And we have a great little workshop on Git, sort of a couple of hours that should get you enough of a start to do most projects. But even if that is maybe a little bit too much for you right now, just keeping your code in a cloud storage or cloud sync folder like Dropbox or Box or Google's or Microsoft's versions of those things, just so that you can potentially roll back a change or two, and if something bad happens to the computer you're working on, you still have your work saved. So those are the two most important things that using Git and a cloud provider like GitHub would do. Is it helps you sort of roll back changes that you made. And yes, Christine also points out that LinkedIn Learning, which you have free access to as someone associated with Yale, also has some good videos on those. But just so that you can roll back changes or keep track of your changes, and that you don't lose all of your work if something bad happens to the computer on which it is stored currently. And I think, I don't know if they're doing it again, but the library did have a tutorial on how to distribute our packages. I don't know if they're offering that again. And if they're not, I might take this out until we put together our own. Questions so far? Okay. So a lot of folks I sit down with sort of immediately assume that when they start talking about R, that it means that you don't care about speed, and that R sort of inherently is quite slow. And you know, it's hard to compete in a language like, in the kinds of languages to which R is a member, but compared to compiled languages like C or C++. But the nice thing about R and Python and some others is that they were designed with the idea in mind that your time is sometimes more valuable and more important than the computer's time. And so if you can put together a program in a day that might have taken you a couple of days or a week to write in C, that's a lot of valuable time saved. And unless it's being run, millions of times across hundreds of thousands of computers, maybe it doesn't need to be the absolute most efficient possible. And really awful speed problems in R are oftentimes avoidable and the result of bad programming practice, rather than actually R just being really slow. And if you truly care about performance but still want your code to be runnable in R, there are a few options for writing code in C or C++, or if you are inclined, even Fortran, and then calling it in R. Another big thing to keep in mind is that sort of as you're prototyping, as you're developing your R code, I strongly recommend that you try and keep a sort of a more goal-oriented focus until you're finished and you have a product that achieves the results that you're interested in. And then only after that, maybe you should start to consider some of the more specialized performance packages. So someone else did some performance optimization for you. Examples of these are data.table and big memory for really large objects, dplyr as a way to manipulate your data in more straightforward ways than you might at first. Some others involving interaction with databases. And then finally, if you have parts of your code that can be accelerated just by offloading a bunch of independent and potentially parallel tasks, there are options for that as well. On the clusters, we sort of bolt this in, but there are a couple of ways to do it on Windows and Mac machines as well. But especially if your code is doing a lot of matrix math, or if you're doing lots of like linear regression, sort of anything built on top of that, you might be able to get some good speed up just by switching out the math libraries that are underneath R. So R sort of comes by default with some fairly simple ones that don't necessarily take the best advantage of the hardware that it's running on. And I'll talk a little bit about that later. And then finally, if you have an R script or a project involving R where performance is quite important, I recommend against using a GUI, specifically RStudio, because all of the niceties that it affords when you're developing code cost something when the code is executing. And so if performance is more important than anything else, but you still want to use R, recommend once you're done writing it with RStudio, adapting your code. And if it's just as simple as like saving it as a .r or learning how to make it accept command line options, but making your R code runnable from the command line instead can oftentimes just be a simple and straightforward way to make it run faster. Questions about that? Pause for a second or two. All right, I'll move on to the next slide then. When you are sort of at the place where you care to start tuning your code, again, try and be methodical, but don't get carried away with, if I write this loop in this way versus that way, maybe I could shave up a couple of milliseconds. Again, you might find that a place in your code that catches your interest might not actually be the most important part of your code to optimize. You can use sort of simple tools such as Top or Activity Monitor or Task Manager, depending on your operating system, just to monitor and see, 5 minutes in, is this still using 100% or, some multiple thereof of CPU, or is there something else going on that's making my R code not run quite as fast? Really great way to speed up R is to use vector or vectorized functions instead of loops where possible. And I'll show a little bit about that later. also to avoid duplication of objects. I'll get into this also in a minute, but briefly, it can get quite expensive if you are making multiple copies of really large R objects. R spends a lot of time just making a new copy of something rather than actually executing the command that you asked it to. So I'll show you a little bit about why R does that and how to tell if it is happening in a minute. A really simple way of saving yourself from bad performance sucking loops is just to pre-allocate result vectors or pre-allocate objects where you know the shape or size of the result before you actually make the computation happen. This can save you from really bad things happening, and I'll show a couple of examples of that at the end here. And then you can, if you want, write your own C code. Again, most of the time, the people I work with don't go to such great lengths, but if you, I mean, I think, to be frank, really the only time that one would engage in that is if you're interested in publishing your code as an R package that other people can use, and you want to cut down on compute time. But I think for most people, if it's just them and or sort of internally their lab, it's not usually worth the time and effort to re-implement a lot of your algorithms as C functions. Questions about that before I move on? Okay. So I want to talk about vectors and matrices. They're kind of weird if you're coming, especially if you're coming from a lot of other programming languages, but they sort of underlie most more complicated data structures in R. And not only are they sort of the framework inside which a lot of R works, but because the language is written around these data structures, there's a lot of optimization that's been put into functions that you would run on them. And so when you can, if you can keep your objects as vectors or matrices, that can lead to sort of an easy way of keeping things simple and fast. Again, because R was sort of written around these data structures, the syntax for doing things to them is often quite terse. R aficionados would call this elegant. You can use a lot of vectorized functions to replace loops. But depending on how you do so, you might end up with quite high memory usage. And I'm sure some of you who are attending are already interested in this specific issue, because I think one of the most common R-related requests on the cluster is, how can I get a hold of several dozen, 100 more gigabytes of memory because my R program keeps dying. It ran out of memory again. So vectors can have all of these things happen to them. So all of the math operators are vectorized functions. So you can add two vectors together. You can use the absolute value, square root, exponent, log, sign, etc. functions on them. You can compare them logically with the single, ampersand, bar, or exclamation point operators, the bang sometimes called, relational. You can, if there are strings stored in your vectors, you can do fun things with them, like the grep and the gsub I really like. You can use the if-else function on vectors, which is a nice, straightforward way of taking a bigger if then else statement and sort of condensing it into a single line and function. And then sort of below, I also just list some other miscellaneous but useful standard R library vectorized functions that sort of come up and sometimes people might not know about. Specifically, I want to call it sprintf and paste, which can be really useful in formatting and putting together strings. Oh, whoops, I can do this, okay. So vectors are kind of strange sometimes. And I want to show some examples of ways in which they're a little bit interesting in R. You might not be surprised. This is sort of a straightforward way of initializing a vector. I highlighted there. So I can just say I want a vector called x that is of size 10 and is the type double. And by default, that just fills, that gives me a vector of 10 zeros. A strange thing that most other languages might complain various levels of nasty about is you can do what's called extension by assignment. So even though x used to be a size 10 vector, I can just assign a value to the 15th thing. And R says, oh, okay, that's fine. I'll just make this vector longer and then give you a value of 100 at the place that you asked me to. I can also, in what might appear as kind of a backwards way, resize vectors by assigning a value to what is returned by the length function. So here I'm now resizing and truncating x to just be 5 long. And you can also sort of directly assign the results of functions to vectors. So here I've overwritten x with 10 new values from the rnorm function. R gives you some simple but powerful ways to talk about subvectors. You can extract them in a relatively straightforward way, just using this syntax. Here I'm saying I want the third to the sixth elements of this vector. I can also use some simple comparisons. So here I'm asking for all values of x where x is greater than 0 and having R return those values with, you know, just a handful of characters. And on top of that, you can do the same kind of strange thing that we did with the assignment of the length. You can assign values and R will reuse them in this case. So in any, here I'm asking for all values of X where is.na is true, meaning I had not a number value for those, and I'm assigning 0 there instead. So this is a relatively straightforward way of taking maybe some input data that you have where NA values should actually be 0 for the purposes of some statistical method that you're about to use. This is a really, elegant way of setting all of those values to 0. Questions about vectors? All right, cool. So next I'm going to talk about matrices. They are basically just n-dimensional vectors. I can create a matrix with a matrix function, giving it some values. So in this case, I'm just asking for 100 values and then reshaping. 1 second. Oh, so I'm going to go back one slide, and I was asked for a little bit more explanation of the logical index. This here. So what's happening on this line is if you just look at the statement inside the square brackets, if you were to run this in an R session on some vector called x, you would get back a logical vector or a vector of true and false values where that is of the same length of x. And so by passing that true false vector as an index to x, I get back only the values from x where I specified true. So this is a way of asking R to give you all the values from x where some logical statement is true. Good question. But so back to matrices. They can be constructed from vectors here. So you see that I've run the rnorm function again, but this time asked for 100 values. And I'm just going to make a square matrix of 10 by 10. And I'm going to store that as the value m. You can use similar syntax in extracting smaller portions of your matrices as you can vectors. So here I'm asking for the third and the fourth row. Matrices in R are row major, meaning I talk about rows then columns. So the third and fourth row and the fifth, seventh, and ninth columns. So here I'm just asking for non-consecutive values. I can also sort of reverse these two and get the fifth, seventh, and ninth rows and the third and fourth columns. My screen is blurry. I'm not sure what else to do other than wait a little bit. I could get a quick yes or no poll in the bottom of your window. If you see, does the screen look good or does the screen look blurry? Yes for good, no for blurry. Oh, 'tis blurry. Let's see if I just unshare and share again. Maybe that will help. Let's do that. Can you get yeses for if that looks any better? Okay, cool. So just go over the last thing that I was showing. You can extract portions of your matrix, both with consecutive or non-consecutive values specified in either of these ways. Oh, and I forgot to mention at the beginning, but both vectors and matrices and everything else in R starts counting at 1. Oftentimes, a lot of other languages will start counting things at 0. And, you know, there are pros and cons to each method, but as long as you can keep them straight, you shouldn't have too many problems. But R starts counting at 1, so the first thing is index 1. You can also take portions of your matrix and convert those into vector form with the cbind function. You can also use the same syntax that we discussed with the vector. So you can pass logical vectors to your matrix and get back values. Here I'm just using the head function, asking for the first 10 values so that it doesn't flow off of your screen. And you can use a matrix index like all values from M that are in A. Again, you can use this strange syntax of assign 0 to all of these values in this way. So next I want to move on to talking about how R thinks about memory. Before I do, are there any questions about vectors or matrices? All right, I'm going to keep going, but if they do come up, just holler in chat and we will pause and go back. So again, from a sort of considering how to write better R code, if you know that some object is big, like say you have a big data frame you just read in, try not to make several different copies of it. I'll talk a little bit about some more memory efficient libraries, and then also a couple of other formats that you can store large data sets in that might help you be able to run R where you might not have if you just, oh, excuse me, we're reading in your entire data set into a data frame, for instance. So R, even when you try not to, likes to duplicate your objects. And this is because R is sort of like a language design implementation decision that was made. it uses what's called pass by value semantics for function arguments. And what that means is when you call a function in some other languages, especially like C and in a lot of cases in Python, those are sort of like my two comparisons. What you will oftentimes get instead of a copy of an object to be worked on is actually just the address pointing to the original object. That's nice because you don't have to wait until a new copy is made of the object that should be worked on, but it can be surprising if you were expecting to not be able to modify the original object. So R sort of makes the decision to be a little bit safer and not risk ever modifying the original object accidentally by passing its value rather than its location in memory. And the downside to this is that oftentimes, especially temporarily, you'll have double the memory usage of something depending on the function that you're calling. But where possible, R will try not to copy things if it doesn't have to. And I'll give you some examples of how it gets forced to make copies. So there's a really helpful, and this is the sort of the most down in the weeds thing that we're going to look at. There's a really helpful function called tracemem, and it helps to track an object's sort of lifetime based on its location in memory. And so going back to our original vector example, if I create a new vector of length 10, that is 10 zeros, and I call tracemem on it, I'll get back this strange looking string, and what that is its address in memory right now. And so everything on your computer while it's running has an address that kind of looks like that, and that's where it's stored. And so if I run this next command, what you might think, based on what I just said, is that a new copy of x would be stored in a variable y that is in a different place in memory. But R has sort of a simple way of knowing, are x and y different yet? And if not, why not just point to the same place? And so until y needs to be different from x, they will both point to the same place. But when I want to change something about y, say I assign 10 to the first value of y, tracemem will give me this this message saying that the object that was stored at this place in memory, so you'll see this and this value and this value are the same. So I'm talking about the original object. I had to make a new copy of it so that I could give the old one a new value and give it to y. I hope that makes sense. The way that R keeps track of whether it needs to duplicate an object or not when its values are modified is with what it calls the name bit. Again, this is not something I normally do when I'm writing R, but this is sort of a curiosity, a way of better understanding how R decides to make copies of things or not. With the .internal inspect functions, you can look at sort of some low-level things about an object. So here I'm getting address in memory, some other things that I'm not going to talk about today, but this this num and then a number. So if that number is above 1, this object has to have a copy made of it before I can modify it. And that's because every time I assign a new variable to this same location in memory, that number goes up. So you see, Y, on the other hand, doesn't have any, I didn't assign anything else to the same values as Y. So right now its named bit is just 1. And I won't have to make new copies of the data stored at the location where Y is until this named bit gets counted up by 1 or more. The sort of annoying thing is, at least, what is this? This presentation was built with R 3.6. So, and I don't think there are any major plans to sort of revamp the way that this works. But once this number goes up, it doesn't usually ever go down again. And so you could consider the variable x kind of poisoned now. If I want to modify x in any way, it's still, because it's not sure who else is looking at this exact same place in memory, it needs to make a new copy of it every time I modify it. So if I wanted to change the value of the very first element in x to 50, I still get a new copy of the thing. Questions about that? Let me go back one so I can do this. And so in practice, so those are sort of like very simple and contrived examples. In practice, how this can be useful to you is, especially if you're dealing with a very large object, thinking about the order that you call functions on it and the order in which you sort of take portions of it and do things to those portions. Here I'm making a relatively simple matrix of zeros that is 3 by 3. What I do then is call the tracemem function, and I get a new address in memory. And here I'm assigning 1 to the first row, first column in the matrix, and you'll see that I didn't get a tracemem call because, again, this is the only place where I've ever referenced m. Its named bit is still 1. I can do to it what I like, but then I call the function nrow on m. And the nrow function just returns the number of rows that a table or matrix has. So here I get back the value 3, and then I want to change m again. So I try and make the first row, first column value 2 now instead of 1. And I get the message from tracemem that I had to make a copy in order to change those values. So does anyone understand what happened? Why did I get a new copy made of my matrix? I didn't assign it any new, I didn't point any of my other variables at m. Why did a copy had to be made? Christine, for the next time we do this, I'm gonna have to get like some Jeopardy music. So, unless anyone comes very quickly into chat and tells me, I'll just spoil it for everyone. It was this nrow function that poisoned my matrix. So before, recall I said that R passes values by, R has a pass by value semantics for its functions. And what that means is when I call nrow on my matrix M, I'm actually implicitly assigning a new variable to M because it gets a copy of the values in M when I call that function. And so anytime I call, let's see, what a non-primitive function. So R calls any function that isn't purely C, a non-primitive function, and functions explicitly only written in C, primitive functions. So anytime I call an R function on an object, there's a copy of it that might be made. So again, if I'm not changing anything about the original object, there won't be a copy of it made until I, again, try to change something about that object. That's what sort of, it was surprising to me when I learned this, when our former colleague, Steve, sort of walked me through how this works. And what this means is that, so say I wanted to make sure that maybe this matrix is 1,000,000 by 1,000,000 rows and columns. Maybe I want to do the manipulation to it before I start calling functions on it so that afterwards, each modification I make doesn't have to be on a duplicate version of that actual piece of data in memory. I hope that makes sense. And sort of just defer your function calls on large objects until after you've done what you need with them, would be, I guess, the practical takeaway from this. The other things that so I want to go over some other things that you can do to try and mitigate the oftentimes large footprint in memory that R occupies. First of which is just, where possible, splitting your problem into smaller tasks. So say you have a data table that is a bunch of different, that has some sort of hierarchy to it, like maybe it's a state-by-state thing. Maybe you could split it up so that you have different instances where you only work per state or per 10,000 rows. This kind of splitting up of data where possible also makes your task a lot more compatible with what the computer scientists would call embarrassingly parallel computing techniques. So if your data allows you to split things up that way, you could even run those on different computers or on different cores on the same computer and achieve really simple but multiplicative speedups. There are some straightforward packages. I like for each, but there's also one called iterators that help you do the same thing, but maybe a little bit less manually. And then you can also, sort of before you read your data in to R, use Linux commands like split or awk, or other languages that might be a little bit more efficient at pre-processing your data. Some examples that I give here. I have also started a tidying data class where we talk a little bit more about this, but you could split your data up into just different chunks, or before R even ever sees your data, you could remove unneeded columns or rows, sort of just cut down on how much memory R has to use on the data that you need to do analysis on. I don't think if you are doing science with R, you haven't seen read.table. Everyone's seen it and used it, and it's really nice. It's a really nice function. It does a surprisingly good job of reading data in for you, and as long as it isn't huge, you don't often have to give a second thought to its use. But when your data are larger, it's especially bad with really wide tables, meaning lots of columns. Read.table slows down a lot, and it's because of sort of all of the pre-processing and guessing it does on your behalf when reading large tables in. It tries to, it basically does a few passes of reading the thing in before it does the real one, so that it can guess at the kinds of data each column are, and a couple of other things. If you want to speed up read.table by itself, the simplest way you can do that is there's an argument called call classes that you can give data types to, and that will tell read.table that it doesn't have to guess for you, and that can speed things up significantly. You can also use call classes to sort of implicitly skip columns, which is another way to use less memory. So say you only need the first 10 columns from your big data set. If you just give call classes the first 10 values, it'll give you a smaller matrix or data frame to work with and less memory to be used. You, especially if you're just prototyping your functions, can just read a smaller chunk of a file in with the in-rows argument. So say I'm not ready to do my full analysis, I just want to make sure that the commands that I am putting into my R script will work. Maybe I only need the first 1,000 rows of my data set. It would probably also make any functions that you call on your data frame happen a lot faster too. If you want to get really low level, there's a scan function where you can go through files in a more low level way. But there are also different packages that provide other ways of reading in data frames or data frame-like objects, and I list those here. Read R is part of the tidyverse set of packages. I'll show an example of using that. Data.table and big memory are both provide ways to read really big data frame-like objects, but they aren't quite data frames. And then SQLDF gives you an object that kind of feels like a data frame, but you can actually run SQL queries on, and you can sort of attach it to a database, and therefore you can have a really big data set that you're working with, but each time you would work on results from a SQL query, which can be really nice. So I have a little example CSV that I just Googled make fake data set or something, and had it just make a bunch of made up people and a little bit of information about them. This is, again, stored in the GitHub repo for this presentation. And this is just the first 3 lines. So it has column names, it's comma separated, and there are different variable types. Some of them are strings, some of them are ages or numbers, some of them are dates. So a really simple comparison that you can do. I wouldn't consider it like rigorous or scientific, but if you just wanted to back of the envelope decide which function to use in the short term, this is a really great way of doing a really simple benchmark. You can wrap a function call in system.time, and it'll tell you how long the user or you took to run this thing, how long the system or the kernel took to run this thing, and then the total time elapsed. Not gonna have time to get into the difference between these two things, but I think usually the thing you care about is the total amount of time that it took to run your function. And so a simple read.csv call on this CSV file took my poor little laptop 1.3 seconds. So, I mean, normally day to day, I don't think that would matter, but if I had to do this 10,000 times, those seconds start to add up. If I just modify that call a little bit to tell R ahead of time all the different classes of the different columns from this data file, I've really, if you look at it proportionally rather than sort of absolute values of how much time humans care about, I can really cut down on the amount of time that it takes to read this file. And so, again, it can vary based on the kind of storage that your data are stored on, what else is happening on the computer, and some other things. But just know that this is a really straightforward way to really speed up data I/O. And then I believe I also have an example of reader. So reader does a lot of the same things that read.table does, but I've found it to generally be about as fast as the example here, where I explicitly specify each of the column classes. So that took 0.24 seconds. And with reader, I didn't have to specify, although you can, and depending on your system, etc., it might speed things up to even a little bit more, but I sort of get about the same elapsed time with reader that I did when I had to do a little bit more work myself. And so this is sort of an example of I didn't have to do very much optimization. I just had to know that reader's read underscore CSV function can be a bit faster than sort of the built-in R read.csv function. Questions about reading tabular data? Okay, I'm going to continue on, but if you're currently typing, keep doing so, and I can always go back. So again, some other ways to read in tabular data into data structures in R that are a little bit more memory efficient. The data.table package is a bit more memory efficient, but you lose row labels. So if something you're doing depends on row labels, this might be a no-go, but the data.table package is something worth looking into. Big memory is a great way to read in matrix-like objects that are mutable, meaning they went kind of far out of their way to make are unable to make a bunch of copies of these data objects. And so it might behave in ways in which you're not used to if you're really accustomed to the way R works, but it can be very memory efficient for really large things, because you will have sort of one copy of your data that you're doing things to over and over again. Big.matrix is a way to operate on a file that's what's called memory mapped, or it actually wouldn't fit into memory if you read it all the way in, but it basically builds itself a little table of contents of your data. And so when you ask to do some function, it will take a bit longer because it has to read things in and then sort of purge those things and read more things, et cetera, et cetera. So there's more I/O that has to happen, but if it's the difference between being able to execute something and not, it's a good option. There's also a package that I haven't looked into in a while, and so I don't know if it's still well maintained, but Big Analytics, which has some neat functions built in with the big LM and the big k-means. Another way to save yourself some memory and some speed or some execution time is by saving your objects or even your entire environment as the R binary formats. This is that message you'll sometimes see when you quit R and it asks if you want to save your environment as like a .rdata file. You can also just save individual variables or objects as R's binary format. I believe it will usually be okay to read and write them between different minor versions, but you might not always be able to read and write those files between different major versions. What I mean by that is a binary file that you wrote with R 3.4 probably won't work with R 3.6. But if you're using the same version of R, this can be a great way to take some intermediate results that took a while to generate and not have to recompute them every time. As sort of like a way of checkpointing for yourself. So you could maybe put some logic into an R script that you're working on where, if this checkpoint file doesn't exist, then run this thing that takes a while. But if it does, just directly read it in and start from there. You can also, if you have any background in SQL or SQL, but maybe you don't want to or don't have a simple or straightforward way of running a full-blown database server, you can take a data frame-like object and store it in a database that kind of feels like SQL with SQLite. and the R SQLite package is a really nice way of interacting with that database. The nice thing about storing your data in a database like file with SQLite is that you can define more interesting relationships between, so you can have a more complicated data structure, and you can share that database with collaborators who might not be using R, but who do have a way of interacting with it via SQLite's other interfaces. So there's like C hooks for it. There's Python ways of talking to it. SQLite also distributes like its own command line interfaces to that database. So it's a nice way of having a little bit more agnostic central source of data. But because you are dealing with a couple of additional layers between you and the data, it can be kind of slow compared to, say, just a data frame already in memory. So again, it's a little bit of a trade-off. You recall before I made reference to the libraries that R uses for math. I haven't tested the macOS version of those commands in a while, so if anyone is running the latest macOS and feels adventurous, feel free to give that a shot and let me know how it goes. But the idea behind this is that you can use either an open source version or Intel's math kernel libraries, which know how to feed specialized linear algebra functions to your CPU, and you can achieve, again, if your R scripts are using a lot of functions based in matrix math, you can achieve a good speed up. So here's this old, tried and tested R benchmark for various matrix math functions that are in sort of the base R. And again, on my laptop using a little bit older version of R than is currently out, but you should see similar results. The default way that R runs those functions took my computer about 30 seconds to run that benchmark. And then when I installed OpenBLAS, I got it down to 3. So again, I didn't change anything about this benchmark. It's sort of a pathological case, so you probably won't see a 10x speed up in your code. But if you're doing sort of matrix math, linear algebra kinds of things in your R code, you might not have to change anything and still get some performance just by using a different library underneath. Okay. Before I continue on to a few examples of how to profile and benchmark, any questions about memory management, some of those extra R packages, these math libraries, etc.? Okay, Scott says in chat that the --with--open_BLAS flag isn't allowed in Homebrew anymore. It might just be the default. So maybe R is as fast as it's going to be for you on your Mac if you install it with Brew, which is good. That means that you're sort of already using a more performant R than you might have otherwise gotten. So I have another question, which reads, I often run out of space after executing some big files and the system hangs. Apart from running the GC command, or the GC function, which is forcing garbage collection, how to make memory management efficient. So apart from the things that, so I guess just to recap, you'll want to, let's see if I can go back here. So referencing our example of sort of the low-level ways that R tracks how and when objects should be duplicated and therefore use more memory. Where possible, if you can defer calling functions on them that have R code in them, and you can look this up, or just try not to call any functions on something until the very end. But if you're going to be doing both modifications on that object and function calls on that object, to try and do sort of your parts to that piece of data first, because otherwise, after you've called your function, you're going to have to have R duplicated every time afterwards, because your R object is passed to that function as a copy, and that copy forces R to increase the named bit associated with that R object, and therefore R can't safely assume that modifying it would result in everyone seeing the right view of the data. So there's one, again, splitting your larger piece of data, or your larger data set, into smaller pieces where possible is, maybe it's a cop-out, but it's a really great strategy. And then looking into some of these other libraries that have more memory efficient representations of the same data can also be a good way to make better use of the amount of memory that you do have. I suppose one thing I don't talk about in this presentation is to just get more memory. That's harder to do maybe on your laptop, where the sticks of RAM oftentimes are even soldered onto your computer, but on the clusters, we have most of the compute nodes, or the servers where jobs run, have at least 100 or so gigabytes of memory available for you to run on a single computer. And there are even a few compute nodes or servers for running jobs that have something like 1.5 terabytes of RAM. And so sort of as a last resort, we can give you access to those, where maybe the most efficient way to get results is to just run the possibly less inefficient R code on the computer and make it do a little bit more work, and then we, the humans, can use our brains for more interesting tasks. I think the last comment I have about that question, running the GC function, R has gotten better about knowing when to run garbage collection. And so sometimes you can actually slow down your code significantly if you're calling the garbage collector explicitly a lot. But again, that's something that has changed more between versions than I have kept up with well. So I guess your mileage may vary. Yeah, and to get access to the clusters, if you don't already have access, I'm just going to give a little plug for us. If you go to research.computing.yale.edu and click on the support tab and that account request. After you fill that out and your PI says, yes, my student or postdoc can have access to the clusters, you'll get an account, and we have a bunch of documentation, and then you can talk to me and I can help you, and you can have silly amounts of RAM and never worry about it again. But I digress. I'm going to talk next about profiling and benchmarking. So sort of as an order of things, order of operations, what I'd recommend is after you've written your code and you're happy with the results it produces, but maybe you're not happy with how fast it produces those results, the first thing you'll want to do is profile your code. And what that does is it tells you the places in your script or your sort of set of R code where it's spending the most amount of time. And the good thing about that is it's an empirical way of determining which parts to spend the most time trying to optimize, because that will obviously give you the best sort of return on your investment, which in this case is usually time. Once you've decided which pieces of the code that you want to optimize, you can then write one or more alternatives that achieve the same result and run benchmarks, which will tell you, which of these three functions that I wrote, which produce the same result, will do so in the least amount of time or the least memory usage, or whatever your thing that you're optimizing for is. And to start with that, I'm going to talk a little bit about a couple of profiling packages. One is called Prof Tools. It's old, tried and true, and I'm sorry, yeah, Prof Tools, and a newer one called Prof Viz, which has really nice integrations into RStudio if that is your IDE of choice. But first I want to go over how to use Prof Tools. So this kind of obnoxious example is just some functions that we tried to make as complicated as possible so as to not make it immediately obvious where you might need to start optimizing if you wanted to figure out where your R program is using the most time in execution. So here I just have 4 functions, and they call each other in various ways. And someone who knows a decent amount of R could sit down and look at this and say, I tell you that function mystery, because I'm not going to tell you yet, is where it'll spend the most amount of time, and that's where you should try and figure out a better way to do things if you really want this to go faster. But you can have Prof Tools sort of do the hard work for you and watch it execute, and then examine the results afterwards and decide what to try and optimize for. And so the way I will often run our Prof Tools is have it, especially if I can afford to do so, have it run some function a lot of times, and sort of by there you can hopefully smooth out any variation in runtime because of everything else that's happening on your computer. And so here, what did I do? Did a million times because this is really short, but maybe if you had something that would take, 10 minutes, maybe you would just do it 100 times and let it run overnight or something. And then has this kind of archaic way, you start rprof and give it the name of the file to which it should write its performance metrics, and then have your function run sometimes and give it some data. So this is kind of a long vector. And then when you're finished profiling your function or set of functions, so sort of everything in between the rprof turning it on and giving it a file, and rprof null, meaning you're finished, clean up and write the rest of your file out. You can then, either in the same session or a different one, load the rprof, the prof tools library, and call the summary rprof function on the file that it writes, and it gives you a data frame with some other stuff in it. And so here I just asked for the table that's by self, meaning I want to see sort of the percent of the total runtime that each of the functions that you saw spent. And so here, what I end up seeing is that both most of the total time and the total percent of time is spent in the function h. And so if I go back to h, you see that I have this for loop where I'm doing something kind of silly, sort of iterating along a long vector and doing something for each individual item. And so that's taking a while to do. I can do something similar with profviz. So profviz is a little bit simpler to wrap around your R code. You just literally make the profviz function wrap around whatever you want to see the performance of. Oops, that would be what I'm measuring the performance of. And this, if you had RStudio running, you would see this sort of as a pop-up in one of the frames, but I was able to extract and save it here. And so this is a little bit less helpful because I've taken, if I just copied and pasted all of the code that I showed you, it would be a little bit more informative, but you can get this flame graph where it'll show you sort of the memory usage and the amount of time each portion of the execution took. But if I go to the data tab, I can see sort of a hierarchical representation of the amount of time. And so you see of the 1890 milliseconds that the function f took, nearly all of that was actually spent in the function h. And so in both cases, the goal is to find the place in your code where the most time is being spent. And if it wasn't already clear, this is another good argument for having your code modularized into functions so that you can better isolate the pieces that you might want to optimize when you're profiling. Questions about prof tools or profviz? Okay, cool. Well, strongly recommend using either. I was just helping someone who was trying to figure out how to get a brain imaging pipeline to run faster. And I wrapped prof tools around a few of the scripts that they were running, and you know, it's several hundred lines of R, so I could have dutifully studied the entire thing, or I could box it up in prof tools and send it off. And the next morning I had a really good summary of which pieces that were spending the most time, and we really quickly were able to narrow down where the humans should spend time figuring out better ways to do things. So again, really great empirical way of deciding where to spend your coding time. So once you have isolated the thing that you want to try and optimize, the next thing to do is to compare some new ways to achieve the same goal. And that's what you do with benchmarking. I sort of already showed you a simple way of benchmarking, which is just wrapping the system.time function around a piece of code that can get a little bit cumbersome if you have several different functions that you want to try all at once, or if you want to be just a little bit more systematic with collecting the results from your benchmarking. And so there's also a nice little package called microbenchmark, which is a good way of comparing, several different ways of achieving the same result with functions. And I want to talk about using the microbenchmark package in the context of some looping examples. And I think it is maybe an oversimplified adage for R that loops are bad and you should avoid them at all costs. And it's not really true, but loops are a great way for common mistakes to really punish you. So I want to show a couple different versions of functions that in the first example, I just want to create a vector of length n where all values are some number. And so here is an example of like the pathologically awful way of doing this. I have a function I've defined where I'm making a result variable that I start out with a null, and then I am iterating for each value from 1 to the length that I want this vector to be, and setting that index of that vector to be some value x. And why is this bad? Well, the first reason is each time this line runs, I am forcing R to make a new copy of the vector called result, because each time result has to be lengthened by 1. Because I never explicitly told R how long result will be eventually. And so R is happy to make result longer for me, but each time it does, it has to make a brand new copy. And doing so will balloon my memory usage. Again, in this simple example, most modern computers would handle this fine, even for relatively large values of in an X, but it will really slow things down because I'll end up with a bunch of smaller vectors floating around in memory that don't have any variables pointing to them anymore, and eventually garbage collection will come and pick them up. But the garbage collection sort of loop in R is not computationally cheap either, which is why this loop would probably be even slower if underneath this line I ran the function gc open close parentheses. Maybe it would make memory usage a little bit lower, but in both cases, I probably just shouldn't be doing the underlying thing, which is initializing a vector in this way. And so here's a slightly better way of doing things. Here I'm pre-allocating my result vector. So since I know the length that I want, I'm going to make a vector that's already the right size. And that way, even though I'm doing lots of tiny little things, at least I don't have to grow and copy my results vector each time. This is my OK.for function. Here is a tricky one. This function kind of looks like the bad one, but I will spoil it and tell you that it performs like the OK one. And can anyone spot why this function isn't as slow as the bad one that I showed you? Right, so a couple people point out that because I'm actually starting at the largest value and going down, I am in a slightly sneakier way making my results vector the right size the first time this loop executes, and then decrementing or going backwards through. But it's still a lot of work done in tiny steps. So here's another way of doing this. I can pre-allocate my results vector, and then here I'm doing that strange syntax that I showed you before, where I can index on a matrix or vector and assign some value to all of the parts of that matrix or vector that are the result of that index. And so if I just ask for all values with this empty square brackets, I'm just assigning the entire vector some value. And finally, I could just use a built-in function called rep, which again, our documentation is not pretty, but if you just take an afternoon and maybe just, I really like the sort of our release, our introduction. If you just sort of page through it some slow afternoon, you might learn something new that you thought you had to use a special library for, or you had been doing a slow way. I know I have in the past, but in this case, there's a built-in function for that, and it's called rep, and it creates a vector with value x n times. And so once I've constructed my different functions, what I can do is give myself some sample data. And the first thing I'll do is run the different functions with my sample data and prove to myself by pairwise comparing the results and asking that they are identical. So for trues means that bad is okay as, bad is the same as okay, and bad is the same as strange, and so on and so forth. So if I'm wrong everywhere the same way, or hopefully I'm just right, and I'm producing the desired result several different ways. So to use the micro benchmark package, what I can do is pass to micro benchmark function. I can name my function something shorter if I want, but I can call function and values for each of the functions I want to test, and it will run them for me. And this extra little wrapper thing is just to make this table kind of pretty for the presentation. But if I ask for a summary of the results from the micro benchmark, and in this case, I'm asking for relative units because I just want to know which one's fastest, not exactly maybe how many microseconds each thing takes, because that matters less as I might be using multiple computers for the same project. You can see maybe going by means that the vector way of doing things is on average 2 times slower than the built-in way, and okay and strange are maybe 40 times worse. And the very worst way of doing it, which was growing my matrix each time and making a copy of it, was almost 100 times worse than just using the built-in function. So in this case, the loop was bad because we were doing lots of really small things that had to take a lot of time to think about doing, where we could have just been using a built-in function that was likely partially or completely written in C that is going to just blow away the rest of the things in terms of performance. Questions about that first benchmark? Oh, I think, yeah, so if you have ggplot2 installed, the micro benchmark package will also plot your results for you as a little violin plot. So in this case, now I'm using time, although I think I can also have a relative x-axis. But you'll see that I can see a distribution now of execution times as well. I wanted to do one more example, this time with a matrix, and it might look similar to our first example. Here I'm going to make a matrix with n rows and x columns, and I want it to be sampled from a standard normal distribution. So again, I don't know does everyone understand why this is the bad way of doing things? Can I get like yeses and nos? Couple yeses. And it's bad again because I keep having to make copies of this, and making copies of my R objects takes unnecessary amounts of time to do so. So my okay way of creating this matrix, I've pre-allocated my matrix here, and then I'm going row by row, and so maybe that'll be a bit faster. Here what I can do is directly return the results of an lapply function. So here I'm basically doing the lapply version of this. So here's a good example of taking a for loop and turning it into lapply function instead. And then finally, the big reveal is that matrices are actually just vectors that have a little bit of extra metadata about their dimensions, but they're stored exactly the same way in memory. So I could actually just make a vector that is the right size and then just change its dimensions. And there I have my matrix. So again, I want to convince myself that all of my different functions are returning to me the same results. And in cases where you're generating pseudo-random numbers, what you'll also want to do is, however your random number functions understand the seed number that they're using to start from generating, to make sure to set that to the same thing for each of your functions. Otherwise, you hopefully won't get the same results. But so here I'm just setting the seed so that I should have deterministic generation of those numbers. And yes, they are all returning the same result. But did anyone catch why maybe one of my functions might not be generalizable? Why it might not work if I change one of these values, n or x? Scroll back here real quick. This is actually a typo that I've left in because it's a good example of a different kind of mistake that you can make. So when I originally wrote this function, I wanted to make sure that when I just ran this code and set the value for n and x, it would give me the right number of values. And then in each row, I'm explicitly calling rnorm with 100. And so as long as my number of columns is 100, this function will work fine. But if I need 101 columns, this function won't perform well. And so it's just a good opportunity to call out, try and minimize the number of times that you specify explicit values and try and always use variables, because here's a good example of a typo that is quite insidious. And also, when you're generating tests, where possible and convenient, maybe try a couple different scenarios to prove to yourself that your functions work in a couple of different ways that demonstrate that they aren't maybe shortcuts or typos. In any case, this was maybe a less drastic depiction of those for loops not being so great. Here I'm only paying time and a half to do it row by row. And so again, if some other part of my R code is taking, hundreds of minutes, and this is just the very beginning, and I find a row-wise way of making a matrix a little bit simpler or some other reason, maybe that's fine. Maybe keep that way. But again, that's sort of the built-in way of generating those values as a vector, and then knowing that matrices are just vectors with some window dressing helped for me to make the best way just a little bit faster. I think, oh, and here's our plot. So really just avoiding the really bad way of doing it, I think would have been acceptable in this case. I'm going to skip this because it doesn't apply as much in, I think, everything after R 3.4. But it used to be the case that R would only just-in-time compile certain functions and not others. That's all I have for today. I will stick around for the rest of our scheduled time for people who have any additional questions. Thank you very much for attending our Zoom session. I think Christine would really like it if you're watching this on YouTube and you like, comment, and subscribe to our YouTube channel. Thank you. And I will now wait for some questions. Oh, even if it isn't set up yet, Christine, I just wanted to say it. I've never gotten to say like, comment, and subscribe before.
Thanks, Ben.